So now let's talk about Dropbox or Google Drive. We all know what Dropbox or Google Drive is. A simple cloud-based file storage service that allows users to store and share files in a more secureable and reliable way, and they can access files from anywhere on any device. That's what a Dropbox or Google Drive does at a high level. Now let's have a look at our requirements, functional and non-functional. The first thing is user can upload file. So the user can upload a file, and user should be able to download file, and he can share the files to whomever he wanted to share the file with. And users should be able to sync files across devices, can be a mobile, web or desktop. And the non-functional requirements that we should meet is we should give high priority to availability than consistency, making sure the files which they have uploaded, it's always there no matter what happens to our servers. And the other thing is we should support large files like 100 GB, 200 GB and so on. And they should be very secure and reliable. They should not be accessible to unauthenticated users and so on, so restricting the file access to very specified users. And of course we should guarantee the user experience is best and latency is as less as possible. Like for example, when user is trying to upload larger files, it should feel it's very fast to the end users. So these are the functional and non-functional requirements that we should satisfy while we are designing the system. So looking at this, it's a simple and straightforward. We can identify the core entities, which is a file and the metadata that we need to store about that file, and the user who is going to perform all of this. So these are like the core entities that we can identify looking at the requirements. Just a simple, the file is basically the raw data that users will be uploading or downloading or sharing, and the metadata is basically that is associated with particular file, like information like file's name, size, MIME type, and the user who uploaded it and all will be stored in this file metadata, and the user basically the user of the system. So these are the three core entities. For now we are just listing it down, irrespective of the columns and the Wagera stuff that we'll be storing. We will discuss more on that as we go deeper into our design. Yep, now we are clear the what are the entities and all. Let's talk about the third step, which is APIs, basically the system interface that the users will interact with. First thing is uploading a file. So we might have an endpoint, something like this, post endpoint called files, and the request that a payload will have the file that the user wants to upload and the metadata related to that file. So this handles the uploading. The other endpoint that we could think of is downloading a file. The endpoint is going to be something like get and passing in the file's ID to this endpoint, and we give the users the file and file metadata along with the file. Okay, so these are like at a high level the initial endpoints. These endpoints might change as we keep progressing in our system design. And the third endpoint that we could think of is share file. Like we discussed earlier, it's basically each endpoint for each of the functional requirement that we have listed down above. The share file endpoint, it's going to be a post and file ID and the share, and to which users the file has to be shared is something like maybe user ID and all is going to be in the form of the list. So this is the third endpoint that we could think of. And the other endpoint we can also think of is basically we need a way for clients to query for changes to files on the remote server. This way we know which files needs to be synced on local devices, which is our the fourth functional requirement. So it can be something like get endpoint, files slash file id changes, and we return file metadata, and accordingly we can sync the files which have changed. So these are the four endpoints that we could think of as of now. Now let's talk about one requirement at a time. So let's deep dive into high level discussion. First point, we know users should be able to upload a file from any device. So that is the thing. So let's try to talk users uploading file flow. In here, whenever we start talking about user uploading of file flow, there are two things that we need to keep into consideration. One, where are we going to store the raw bytes, which is basically the file that the user is uploading, and the other is where are we storing the file metadata related to that file. So these are the two things that we need to consider when we discuss about uploading file flow. For storing metadata, we can use NoSQL database, something like DynamoDB. Why DynamoDB? Because our metadata is very loosely coupled and structured, so it's better to go for it. Or we can choose Postgres as well, but it's not much of a question here which one to choose. It's more about our choice. So let's go with the DynamoDB or Postgres. So I'm just trying to go with the DynamoDB for now. So it might look something like this: the file metadata like id and the name of the file, size, MIME type, and uploaded by. So this is like simple document schema to get started with DynamoDB. So that is the choice that we will make to store the file metadata. All right, now we have chosen where to store file metadata and all. Let's talk about where we are going to store the file. The first point, which is where are we going to store the raw file that the user is going to upload. Let's brainstorm and discuss the multiple approaches and then agree on to the final approach that satisfies our requirements and meets our needs. So file store, the thing that we can directly talk is directly uploading it to our primary server. So what do I mean here is directly uploading to file server. It is going to be simple. Basically we can take the file and try to upload that through our gateway, API gateway, to our primary server, which is the backend server, and store that file in our local file system. Yeah, we try to store that file in our local file system, and then once that is stored, we try to update our DynamoDB, which is a file metadata DB. So this is a like simple approach which we store in server's local file system itself. But the downside of this approach is as files grow, more local file system is needed, and we need to keep adding a more local file system support or more servers. Okay, fine, assume that we have added more primary servers. The other downside is this: if server goes down, all the files that we stored in that respective local file system will also be lost. So that significantly goes against our reliability. We need to make sure the files that the user uploads are reliable. So if the files are losing in this way, if the primary server goes down, it's not reliable. So this is not the solution that we need to go ahead with. Okay, so this is one approach that we can think of. All right, let's talk about the second approach now. Storing file in blob storage, example AWS S3 or Google Cloud Storage or Azure's blob storage. Okay, so this flow is simple. We try to store whatever the file that is being uploaded by the user in our S3 bucket, where the actual raw file will be stored. Simple and straightforward. Here the things that we need to worry or be cautious about in this approach is we need to integrate this S3, which is the blob storage service, with the primary server. The thing that we need to handle is whenever the metadata is saved in this DB, we need to make sure that the file is also stored, and whenever the file is stored, need to make sure the file metadata is also stored. So there can be cases where file is uploaded but metadata is not saved, and metadata is saved but file is not uploaded due to some issues. So that is the first challenge that we need to make sure we take care. And the other problem, which is of a bigger concern for me, is it's technically we are uploading the same file twice, meaning the client uploads first the full file to primary server, and once primary server has the full file, we upload that to our blob storage service. So which is redundant, and it's not a good approach at all, because it's of a more time to the users, and also doing redundant ops in our server consumes more resources, and it's not ideal for a long-term solution. So this is also not a solution to stick to. Let's talk about the third one. The third one is, why can't we upload file directly to blob storage instead of relying on primary server to upload it to blob storage? So let's talk how that's going to happen. So how this going to happen is, we need to leverage a concept called pre-signed URLs. So what are pre-signed URLs? Those are the simple URLs that give user a permission to upload a file to specific location or bucket in blob storage S3, and we can generate that pre-signed URL and send it to the user so they can upload a file. So let's talk about the general flow, how this is going to look like. User is going to pass a request to this primary server through our API gateway to request a pre-signed URL, which gets the URL from this blob storage S3 and saves file metadata into our database with status of uploading and all, and then returns that pre-signed URL to client. And this client now uses this pre-signed URL to directly upload it to S3 via put request, which is how it is designed to upload the file to S3. Once the file is successfully uploaded to S3, we will send a notification by leveraging a concept called S3 event notification to our database to update the status from uploading to uploaded. So that's how we completely delegate the responsibility of uploading a file from primary server to directly client itself. So there we completely avoid a bottleneck, and also the number of steps that the file needs to go through, which drastically improves the performance of our system and provides a best client experience as well. So this is the thing. So the flow initially in the API to upload files will now have 3-step process. One thing is, we try to request for pre-signed URL from primary server, and along with the metadata that gets saved in our DynamoDB, and then we leverage pre-signed URL to upload file via put request to blob storage from client itself directly, and once uploaded, S3 event notifications will update our status in our metadata DB. So this is a simple and the approach that we can completely rely on, and this is the approach that we should choose to meet the requirements. So that is how we are going to satisfy our first requirement, like user uploading the file and make sure we give better experience to the user. Now let's talk about the second requirement, which is users should be able to download the file. So the downloading file flow. So let's also discuss the multiple approaches that we can think to achieve this requirement. The first thing is trying to download directly through our file server. This is a simple thing. Is directly we download from blob storage to our primary server, and then once a primary server has gotten hold of the file, we download from that primary server. That's like a two-step process, from blob storage to primary server and from primary server to the client. Again, here redundant downloads. It's first we are downloading to primary server and then to a client, which is not a way to go and discuss, because we completely want to delegate to client itself rather than relying on primary server. So then the next option is basically downloading directly from blob storage. So here we will directly allow the user to download the file directly from S3. So same way here also we can use the pre-signed URLs to generate the URL that the user can use to download file directly from this blob storage. Like with uploading, the pre-signed URL will give the this pre-signed URL will give the user the permission to download file from specific bucket or location in S3 for limited time, which we can have a control on. The flow it's going to look like this. Here you see the download that we have. We try to download via pre-signed URL directly from S3. So I request pre-signed URL from backend. So this is the step that we have, and try to get the pre-signed URL and then use the pre-signed URL to download from S3, which is a simple way to directly download from blob storage instead of relying on this primary backend server that we have. And the challenge here is this: if let's say users are globally distributed across the regions, and if our blob storage is in a single region, it will still be a slow for a user who is far located from that user, and this goes against our the requirements. Basically they should be able to download as fast as they can, and less latencies is what we should guarantee from our system. Okay, to guarantee the latency is going to be as minimal as possible, it's the next approach that we need to talk about, which is downloading directly from CDN. So what is this approach is, here we try to cache the file closer to user's region. So to briefly talk about CDN, a CDN is basically a network of servers which are distributed across the globe that caches files and tries to serve them to users from the server which is closest to them, which reduces latency and speeds up download times. So here is the thing: whenever user requests a file from S3, we use the CDN to cache frequently accessed files and serve that file from that CDN, so that it feels way faster for a user who is trying to download the file. Same like S3 pre-signed URLs, we can generate a URL that the user wants to download the file, the thing, and cache it near the CDN, and this will give this URL also ensures security and gives user permission to download a file from specific location in the CDN for a limited time. So this is how we can try to address the issue of the latency and meet this second functional requirements. But however, there are some concerns too. The challenge is to be cautious of. CDNs that we are trying to add are not that cheap. They're expensive, and we should carefully handle which files know to cache and for how long. So basically, to make sure that we are not caching all the files, we should only cache frequently accessed files and have a proper cache invalidation to remove files which are either deleted from blob storage or from file metadata or the things which are updated. So this is something, the cache control, the invalidation and updation is something that we need to carefully design when we are trying to add a CDN into our design. Okay, so yeah, with this approach we can satisfy the second requirement. The user should be able to download file and it should be way quicker and way faster. Let's go to our third requirement, functional requirement. User should be able to share file to multiple users. And here as well, let's talk about multiple ways how we can achieve this. First thing, we try to add a share list to our document schema, which we had earlier. Here I try to update the share list, like with to the user IDs that I want to share, and based on this, um, whenever user tries to open a site, we try to just check against this list and see to which users the files have been shared with, and showcase accordingly if the user ID is in this list. The problem here is getting a list of files for a user is easy because we can directly query on the ID which is all indexed on and get that thing. But I mean, because we have the uploaded by, and we can just filter by this and get the files that are belonging to a specific user. But getting the list of files that are shared with them is very slow because we'll have to look up through each document shares list and try to get the user IDs and all. So this way we need to scan the entire share list of every file and see if the user is present or not. So this makes way slower for us to query the files that have been shared with. So this is again not going to meet, and it's going to affect the latency and experience of the user. To avoid that and maybe to speed up the fetching the share list, what we can do is we can try to cache to speed up the querying of share list. So maybe in a cache the key might look to this user ID, these are the files that have been shared with. So now we just need to look for that user ID key and get all the files that have been shared with. Again, this approach also comes with downsides. What is that thing? We need to make sure that we sync the share list inside our metadata DB and in the cache. So that is something we should carefully think about the logic. Make sure the contents in the share list in our metadata DB or in a cache or consistent. So yeah, to overcome this, what is that we can do is basically we need to maintain user to file list mapping in the same database and update both the share list and shared files mapping in the same transaction. That is what our third approach is. We try to create a separate table for shares. It's kind of like we know the normalization that we all learned in our colleges. So we try to normalize the data, that is user ID to file ID mapping. So this way it becomes way clear which file the user is having access to. So but this solves the issue of syncing, not to worry about syncing between cache and the file metadata DB. The query is little bit slower when compared to direct memory access, but that's fine. That's a trade-off we are willing to play with, because the consistency is very important for us than the this one. So that's the one trade-off which we are willing to make a decision. Okay, yeah, this is how we can try to make sure the file sharing is also well taken care of and meets our requirements. The fourth functional requirements in our this system design is users should be able to sync files across devices. So this is something which is way trickier, and let's talk about this. There are two directions that we need to keep addressing. That is the bidirectional. One is local to remote and another is remote to local. So remote is nothing but our cloud, and local can be users mobile desktop or whatever client is. To get started with, let's consider remote is something is always considered as single source of truth for the file to take the update from or update to. Okay, let's talk about first thing, local to remote. So this is whenever user updates a file on their local machine, can be either Mac or Windows or mobile or whatever, we need to sync these the changes in the local to our remote server. So as we said, we consider remote as a single source of truth. So it's important that we keep this one as consistent as soon as there are some changes in our local. So to do this, we need something called client-side synchronization agent. Let's talk about that. For us to achieve that, we need to monitor the local folder, whatever, let's say maybe for folder name can be something like Drive or Dropbox and all. And how can we monitor local folder is basically just leveraging OS specific file system events. So if it's a Mac OS, we can rely on this FS events, and if it's a Windows OS, we can rely on this file system watcher. So when it detects a change in this particular folder, it queues the modified file, the one that has been updated, for upload locally, and then it uses our upload API to update our remote server along with the metadata. So the one thing here is, if there are multiple writes, which one to consider? To keep it simple, let's consider that always the last version is going to win, meaning we always consider the last write is something that is the thing needs to be synced up with the remote. It's not the most optimal way to think of. We need to version that and maintain those versions in our remote servers, but maybe we can not worry about that versioning for now. Maybe you can consider that as like how to scope for this discussion, and just go ahead with this last right wins. And that's how we can try to sync the changes from local to remote. The other direction now, remote to local. So now each client needs to know when changes happen on our remote server. They can pull changes down to their respective local folders. So there are two main approaches that we can think of. One is polling. What is this polling? Client periodically checks, asks like, has anything changed since my last sync? Uh, mm, then the server would query it. The server would query this database and see if any files that the user is watching as updated at a timestamp that is newer than the last time they synced. Okay, this is simple but can be slow to detect changes, and it wastes a lot of bandwidth if nothing has changed, because there will be continuous calls, and which is wasting a lot of bandwidth. The other approach is WebSockets or server sentiments. Here, the server maintains an open connection with the client. It maintains open connection with the clients, and then it pushes notifications to client whenever some change occurs. Uh, this is more complex to implement, but it really provides it really provides real-time updates. So which one to consider for our approach? Best is to make this hybrid, meaning we try to leverage both of them. Mostly the users are worried about the recent files that they are uploaded. So for recent files, user expects real-time updates, or the things needs to be synced locally. So for that, we can leverage the WebSockets or server sent events for real-time updates. And for the files which are way older, where the access to that files is very rare, and for that we can um, rely on polling, since immediate updates are not critical to the end users. So this is how we can make sure we leverage this hybrid approach of syncing from remote to local. So after this is how the design is going to look like. The for local to remote, we watch changes locally and update remote in the client uploader, the downloader. I know they can be the same, but just for representative purpose, I have just added a couple of boxes here. And for downloader, we try to poll for changes in remote and try to sync the thing. So yeah, this is how we can make sure the syncing happens bidirectionally, and makes our system consistent. And that is how we are going to meet the fourth point, that users can sync files across devices. And this is the design, how it's going to look like. Okay, right. Now let's talk about the potential non-functional points one at a time. That is the deep dives. In that, the first point is we need to support larger files. uh, User can come with 100 GB file, 200 GB file, and he should still be able to upload that with, like he used to, with a smaller file. And how are we going to give him the same experience as he comes up with the um, bigger file? So one is progress indicator. That is, we need to let the user know that the upload is happening, and something with like percentage and how long it's going to take and all. And also the other thing that we need to uh, give the user an option is for resumable uploads. um, Basically this is we should support the user to pass and resume uploads, like if they lose some internet connection or they close the browser, they should be able to pick up from where they left off rather than all the way doing it from scratch. So this is something that we need to keep these two things into consideration and try to design our system. Okay, assume like we don't have this, and why can't we make that happen just via single post request? There are challenges. Let's try to discuss about them. It's important that we know the limitations and why we are choosing this one. So why not a single post request? It's because web servers and clients have a timeout settings. So by default they will have some cap on how long they can have a connection. So let's take for example the 50 GB file is something that the user wants to upload. So let's estimate how long this might take to get into our server. Assume the network speed is 100 megabits per second, and the 500 GB 50 GB file over 100 megabits per second, it is going to take 1.11 hours. How? Let's see. 50 GB, let's convert into yeah, from bytes to gigabits. So 1 byte is 8 bits, so 50 multiplied by 8, it is 400 gigabits. And now this gigabits needs to be converted to megabits. So 1 giga is 1000 mega, so multiplied by 1000, it's going to give us the 400,000 megabits. And now we have 400,000 megabits. Let's try to divide this by the 100 megabits per second. So this gives us 4000 seconds. So converting into minutes, approximately 66.67 minutes to hours, it's 1.11 something closer to that, or 1.6 or whatever it is. Okay, so this long is what it's going to take for a 50 GB file or this network speed to get into a server, which is nothing that the user can wait, which is very bad user experience. Even you or me cannot wait for that long, and is just going to not use our service anymore. And another thing is, most browsers and servers will have a limitation on size of the request payload. Max, let's say 2 GB, but here our file is 50 GB, which is clearly not supporting our requirement. And another thing, network interruptions, like either users may lose internet or something, or as such, which completely provides bad user experience if you choose a single post request. That is why we need to address this and break down into chunks, which is an option like chunking on client side, and able to provide a progress as each chunk gets successfully uploaded, and that is what provides a good user experience. So let's talk about one thing at a time. Yeah, the chunking, like let's say we have a 50 GB file, so I'm going to break down into chunk of like 10 MB or 20 MB depending upon the network speed and bandwidth and all, and we try to update each chunk and update progress on the our side, so that user gets a track of the percentage of the upload that is completed and how long it's going to take to upload the whole file. So that's how we are going to address this progress indicator. And the other thing is resumable uploads. How are we going to ensure this is going to be supported? First thing is we need to keep track of each chunk status in our metadata DB example. So we had this one way before till status, and additional thing is chunks. Let's say we have like 3 chunks. For chunk 1, what is the status? Is it uploaded, uploading, or not uploaded? So we need to maintain at each chunk level the status, so that when a user tries to resume the upload, we can check the chunks list and see which chunks have been uploaded, which have not been uploaded, and then we can start uploading the chunks that have not been uploaded. This way the user doesn't have to start all the way from the full file. Okay, all right, so this is how we ensure the uploads are resumable. Now the other question is how to keep these chunks in sync in the storage bucket. So we are in our metadata DB, we are just maintaining the status of the chunk, but actual chunk is stored in the S3, right? And we need to keep in sync between the storage service and our metadata DB. How? Let's discuss about that. There are 2 approaches that we can think of. First thing is the client takes the file chunk set and uploads the chunk directly in S3 that we have, and S3 responds to each chunk with a success message. So here client uploads to S3, S3 responds with success. Now on each success, the client sends a patch request to backend to update chunks field and that respective chunk. So it's more on relying on client to make a patch request to our server and update metadata DB accordingly. So downside is that itself, relying on client to update backend, it's something that we should not consider, because a user can maliciously update backend status through just patch request without actually uploading that to S3 which is a corrupt entry that we are allowing into our metadata DB. So this downside, the challenge just makes really hard for us to go ahead with this approach. The other thing is it's better to rely on the by default S3's event notifications. So what happens here is we can rely on S3 event notifications on each chunk upload. We can trigger the Lambda function or send a message to our simple notification service topic, which we can use this to send a message to backend when chunk is successfully uploaded and update the status accordingly in our file metadata DB. So this is more reliable than the patch request. And now all right, that this is going to ensure the synchronization issue. The other question now we can come up with, or the thing that we need to discuss, is how do we check if the file that the user is trying to upload is already uploaded, is already there in our system, and assume like we somehow figured out that logic. Now we also need to make sure which chunks of that file have already been uploaded and which chunks have not been uploaded. Okay, so to answer both of the questions, the approach that we need to rely on, of course we cannot rely on the file name. I can have the same file name uploaded multiple times for different file content, so that's not the way to keep track of the unique file identifier. So the approach that we can rely on is something called fingerprint. So to give an idea of what is fingerprint at high level, it's simple mathematical calculation that generates unique hash value based on the actual file content. uh, mm, Ideally, that hash value is generated using cryptographic hash functions such as SHA-256, and we take this as a unique identifier of the file and check against our DB, and if that file unique ID exists, we know that the file is already there in our system or is being uploaded before. For a chunk level also, we need to maintain this fingerprint. So this way it ensures that we can at least have a logic to query if the file has been uploaded before or not, if the chunk has been uploaded or not. Okay, so the flow is going to look like when we try to tie all of this together. Client chunks file like 5 to 10 megabytes, and we try to calculate fingerprint for each chunk and along with the full file. Okay, and yeah, client sends a get request to file metadata for the file with the given file ID, which is the fingerprint, just to check if the file ID exists in our DB or not. So let's assume it exists, then we resume the logic of resumable uploads. If file doesn't exist, then client will post a request to /files pre-signed URL concept, which we just discussed, to get a pre-signed URL for the file, and the backend will save the metadata DB with the status of uploading, and chunks array will be a list of a chunk fingerprints with the status of not uploaded. Then client uploads the chunks to S3 via the pre-signed URL which we just gave to the client, and after each chunk is uploaded, S3 notifies backend, and backend marks that respective chunks as uploaded. And once all chunks of a file are uploaded, we mark the file as uploaded. So this is how the approach is going to look like when we try to tie all of this together. So this is here the simple approach. That's how it's going to look like. We try to chunk file and client and calculate fingerprints for bigger files and make sure we support this large files. So that's how we can support larger files upload. By default, AWS provides us multi-part upload, which out of the box has all of the support for chunking and the status updates, progress and all. But it's good to know this is how it's done behind the scenes, and we can leverage AWS multi-part upload. Yep. All right, so that's one of the things. And now the other thing is we need to make sure the uploads downloads are way faster. So how are we going to make sure? We already made sure that we break down into chunks and leverage a CDN to cache a file closer to the user, which really makes faster for downloading. For uploading, we made sure chunking and resumable uploads, making sure it's way faster, and also we can send chunks in parallel depending upon the available bandwidth. So this makes uploads and downloads faster. So it's already taken care. We can not worry much about that. The other thing is apart from that, how can we make sure it's way faster? For syncing, the one, instead of trying to sync the whole file, now we have introduced the concept of chunking. We can just identify chunks which are changed and only sync them bidirectional, the remote to local and local to remote. Okay, and another way to make our system way faster is compression. So we can compress file on client, before trying to send it to our server or storage service. So here the question is which files to compress and which files not to. So let's say like if the file uh, the time it takes to compress a file is way higher than the time it takes to send and upload it to our server, then that's obviously a scenario that we need to go uh, uploading file directly and not go for compression. A good example here is for images. I don't think there's going to be much significant differences, so no need of compressing there. But whereas for text files, PDF files, we can choose compressions. It is going to reduce the size of, like, let's say 5 GB 10 GB file to 1 GB or 2 GB, which it's good for us to reduce the file size so it can be uploaded way faster. And once it is uploaded to the server, we can decompress on the server, and just the vice versa. So yeah, the algorithms that are good for compressing is zip, broadly, and z standard. So most adapted one is zip, or we can just choose the broadly or z standard. But it's also the thing that we need to consider when we are choosing the compression algorithm is it supported in the most popular web browsers or not. Okay. And another is, if we have introduced encrypting for security purposes, it's better to compress before encrypting, because of not introducing in unpredictable random number, and also for much higher compression ratio. So this is how we can make sure the uploads, downloads, and syncing way faster, apart from a CDN and the chunking and resumable uploads that we introduced above. The additional thing it's a good to discuss on. And now the last thing, we need to make sure the file is secure whenever we are in trying to transfer over the network, or when we are storing in a blob storage service. How do we make sure? There are three ways. One is encryption in transit. So yeah, whenever we're trying to share a file over a network, make sure it's always encrypted. So the HTTPS, which we normally consider. And the encryption at rest, it's simple. We can just leverage S3's encryption feature, which will encrypt the file using a unique key and store the key separately from the file. This way, even if some user gets access to the file, they won't be able to decrypt it without the key, which is stored separately from the file. And we do already have the access control, the shares list. So we restrict the unauthenticated users from accessing that by using this shares list. So we limit that. And the question is, what if some authorized user shares a download link with an unauthorized user, maybe over a public forum or so? um, uh, this is not much of a concern, because anyhow we always give pre-signed URLs within a timeout. Even if they get an access to it, it will be expired after 5 minutes or so. So it is not of a big concern, and that pre-signed URL, it's going to take care of that unauthorized users trying to access the content of our authorized user. So this is how we can make sure the file is secure, and it's not easy to tamper with. Yep. So yeah, concluding, this is a brief discussion on our Dropbox or Google Drive high level system design discussions. Though it's not much, but at least given the couple of points in our requirements, we try to reason up the choices that we made and why we made, and made it clear. It's going to the ultimate design that we have, it's going to support and satisfy the requirements. So this is the end of this Dropbox or Google Drive discussion. Next, let's discuss on something like local delivery systems that we normally see, the Blinkit or Zepto, and how can we at least take a couple of minimal requirements and think through and reason up for the system that can support them.